This is a VRL 250 receiver. Just completed the electronic restoration of this set. So some work to do on the paintwork next. The actual front panels of the power supply unit here and the main receiver are actually not too bad, so I'm probably not going to do anything with those apart from give them a polish. But the side panels and the top covers are pretty badly damaged, paint peeling off. So I need to get some matching spray paint for those. Just thought I'd make a couple of short videos. One just to show the set working. It's actually tuned to 10 megahertz WWV at the moment. Using a short indoor active mag loop antenna. I've taken the cover off the tuning capacitor gang to allow access to the grid connection of the mixer tube, and the bottom panel isn't fitted, and this is to allow access into the underside of the chassis to allow a connection to be made to the plate of the detector tube. And the reason for that is I'm going to do a demonstration of checking the IF passband using a spectrum analyzer with a tracking generator. So that'll be the next part of the video. I'll splice the two together shortly when I've got the setup complete. So here's the VRL receiver set up for measuring the IF bandwidth. Tracking generator is connected to the 6K8 mixer tube grid via a 0.02 coupling capacitor, and that is connected to the tracking generator output of the spectrum analyzer through a switched attenuator, set to 60 dBs attenuation at the moment, and the scope probe, times 10 scope probe, is connected through a DC block to another DC block to the input of the spectrum analyzer. And without the crystalline circuit, the selectivity position is at crystal off, and the phasing control set around about 5. That allows bandwidth of around about 5.8 to 6 kilohertz. It's about as sharp as I can get it, and this is really the best symmetry I could obtain by adjusting the third IF transformer. The first two IF transformers are a little bit more sensitive, and once you start playing with them, it really is difficult to get the symmetry right and still keep the amplitude reasonable. So with a passband of 6 kilohertz or so for general AM listening, that's not too bad. It's not quite as good as I'd expect, but not too bad. I have managed by just tweaking the phasing control so I can get it a little bit sharper than this, around about 5.6. But it doesn't really make any difference in practice, and neither does this slight asymmetry. You certainly wouldn't be using this set for broadcast band reception, because it hasn't got a broadcast band. Reception starts at 1.4 megahertz up to 28 megahertz. So very few music stations, so you really just be listening to speech with that. So when you switch the crystal filter in, it's got five crystal positions. It's a single pole crystal filter. You can see it's affected the passband quite a bit. With the spectrum analyzer set for 25 kilohertz span at the moment, resolution bandwidth of 100 hertz. I'll reduce the span, but you can see that the typical crystal shape, response shape, is coming there, and with the phasing control set around about 1, the dip is on the low frequency side. So I'll now switch the crystal filter in. I'll set it to selectivity position 1, and the phasing control is around about 1. So you can see the response curve is now changing quite a bit. It's a bit slow because I've got the resolution bandwidth set at 100 Hz and the span is 25 kHz. I'll adjust the span in a second, but you can see with the phasing control at the lower end, around about 1, the dip in the response curve is to the high side of the peak. And if I swap it round to the opposite end, around about 7, the dip in the response curve swaps over to the low frequency side of the peak. And if I put the phasing control so around about position 5, it results in a single peak and no notches in the curve, which is great for single station reception. You can see it there. So I'll decrease the span. Try something like 5 kHz to start with. That should broaden the curve out. I'll broaden it out a little bit more. Say 2.5 kHz. This gives us better resolution on the peak. So at a -6 dB bandwidth of about 180 Hz at that setting. So now change the selectivity to say position 3. See how that affects the curve. So we've now got a bandwidth of about 297 Hz. And I'll just finally go to position 5. That's reduced the amplitude, and of course it's reduced the bandwidth as well. We're down to 53 Hz at -6 dBs now, which is very narrow. Let's move it to position 4 and set it for a notch on one side of the curve again. So you can actually keep adjusting this until you get these almost perfect reception. You can null out a station on one side of the carrier, or you can just keep a peak. Actually, let's change the reference level here. See the notches on the upper side of the curve there. And let's try position 2. All the selectivity switch does is introduce damping onto the crystal. A series of resistors on the switch. Nothing fancy. See a very deep notch there. Try changing the scale to say 10 dBs on there. You can now see the full notch there. So we've got 10, 20, 10, 20, 30, 40, 50, 60, almost 70 dBs of difference between the peak and the trough, which is really would null out a nearby station. And as you change the phasing control, it moves this curve across the passband. So the crystal filter is working really well in this set. Pretty impressive for a 82-year-old, something like that. Let's change the notch to the other side. Quite a steep on that side. Every crystal is a little bit different, and the circuit is a little bit different, so I found that almost every crystal filter has got unique response curves. So there we go. That's really all I wanted to demonstrate, was how to connect up a spectrum analyzer to a receiver to check the bandwidth. One point I would make is that I've got this isolated just with a ×10 probe and a couple of capacitors, but some detectors, and for example the last I think it was the National I worked on a couple of months ago, it had an infinite impedance detector, and I found that I had to have a very small coupling capacitor, like a few picofarads, in order to get a reasonable response curve. With just this setup here, it was damping the infinite impedance detector too much. This is just a standard diode detector, nothing fancy. So this doesn't load the detector at all. But this probe was loading the infinite impedance detector quite a bit, and it just couldn't get a good response curve on the spectrum analyzer. There we go. So. VRL receiver, VRL standing for Vancouver Radio Laboratories, made in Vancouver, BC, in about 1943, and just been refurbished. All the capacitors have been restuffed. Some resistors have been replaced and kind of disguised. The bathtub capacitors have been restuffed. The power supply, the two kind of electrolytics have been restuffed. So all the capacitors underneath. Made an umbilical cable up for it, and I installed a pair of Jones plugs in there so they can be disconnected quite easily. It's quite a nice receiver, nothing too fancy. It's 2 RF stages, 3 IF stages. And it's got 2 AGC lines, one to the 2 RF stages, one to the IF stages. It's got a very fancy crystal calibrator. It's actually got 3 frequencies on the calibrator, which is built into the power supply unit. It's switched to a 1 meg at the moment, but it's switched off, and then you've got 10 kilohertz, 100 kilohertz, and 1 meg calibration. It's not connected to the receiver at the moment. There's an output on the back here, which you just dangle near the antenna input to listen for the calibration pips. But really, apart from that, it's pretty straightforward World War II style communications receiver. Built for the Canadian Armed Forces, and judging by the colours and some of the literature I've seen, this was destined for the Canadian Army.